Okay. So let's go on page 62. We're still on a 0 point something lesson. So it's some of this is the review. Some of this is me front loading you because I just feel like if we jump in where they expect us to jump in without talking about this stuff, it would just make it way more confusing. So I want to kind of lead you into where we're going. We're going to start talking about radians today, which is definitely something that you talk about in geometry, but maybe just a teeny tiny bit. The angles that we're going to talk about, when I taught pre-AP geometry, I did it because I felt like it was important. I honestly couldn't tell you if it's actually part of what you're supposed to do. So I don't know whether or not some of y'all know this. Some of you may, but I have a feeling that not everybody does. So we're going to go back over it anyway. All right, so you know that we have angles in figures. You've seen angles just floating around in space, but we can also have angles in the coordinate plane, and they can just float around in the coordinate plane. But we're really concerned right now with angles that are in standard form or in standard position. Let me scroll a little bit. An angle in the coordinate plane. So an angle is in standard form or standard position when the vertex is on the origin. So my vertex is connected to the origin right there. One ray lies on the positive x-axis. So this ray right here is stuck no matter what. And then the other ray is somewhere else, but still attached to the origin. It just kind of rotates around. So there's where we get an angle. That angle is in standard position. Okay. So that angle looks like this. And then it took this one and it opened up this way. I can also open up this way, and we're going to look at that in just a second. So this ray here that's on the x-axis, that is called the initial side or the initial ray, either way, but side kind of makes more sense here, I think. It's the initial side because it's where you start. The other ray is called the terminal side because it's where you stop. Okay. And then the direction in which the angle opens is important. Now, I know, unfortunately, the majority of you can't actually read this clock that's hanging on the wall, but hopefully you do know the difference between clockwise and counterclockwise. And if you don't, watch the little red hand tick for a few seconds. That's clockwise, okay? So if we do a counterclockwise rotation, like what this is, like opening up this way, okay, counterclockwise rotations result in positive angle measures. And clockwise, so if I opened up this way and went like that, then clockwise results in negative angle measures. And I'm sure that you were told at some point that you could not, negative angles don't exist or you can't have them. The fact that they don't exist is a lie. The fact that you can't have them is not necessarily a lie depending on the situation that you're in. And that might have been cleared up with some of you, but maybe not all of you. If I have a triangle and we're looking for the missing angle of a triangle and you add them up, subtract from 180 and you get negative 27, yeah, you're wrong because you cannot have a negative angle in that triangle. That does not make any sense. But negative angles do exist. It has to do with the direction in which the one side of the angle rotates around in the coordinate plane. Okay. All right. And like I said yesterday, we really don't deal with degrees at all. The only reason I have degrees in this lesson is because I know they make sense to you and I want you to get the concept and then we kind of make it into radians, also kind of having you relate it. But you having to understand and use the degrees is not really anything that is going to be important to us. But you already understand them, so it's fine. All right, so the most common unit of measure and the most common unit of measure for angles is the degree. At some point, you probably thought that was the only way. How many degrees is a full rotation? 360. So a degree, meaning 1 degree, is equivalent to 1/360th of a full rotation. And this circle is labeled here. So see how we have a 0 here? Because if I had an angle, would start here. And then if I rotated it this way, kind of like that one was, would look like this. And when you learned your quadrants and the way that they were numbered, like myself, you probably thought, this is dumb. Why are they numbering them this way? Because it just doesn't seem to make any sense. But it does make sense because when you start here at 0 and you rotate this way, that's why this is quadrant 1. Then you rotate through quadrant 2. Then you get to quadrant 3. Then you get to quadrant 4. And that's why they are numbered like they are numbered. okay, because you start with all positive, X and Y values, whatever. You start there at 1 and you rotate around that way. That's why they're numbered that way. That's definitely old news. Definitely have to know how that works. Okay, we all good so far? All right, so then we're going to sketch these angles. We're not going to get out a protractor and make them all perfect because we don't care that much. We're just going to kind of ballpark it, but ballpark it as accurately as we can. Here's what I mean by that. This is where we start, okay? That's our initial side. We have a positive angle of 135 degrees, so we are going to rotate counterclockwise. I know if I rotate from here to here, that is 90 degrees. So if I subtract 90, how much farther do I need to go? 45. And 45 is related to 90 how? It's half. So if I go halfway between these two, just as accurately as you can, aim for half. Okay? Everybody okay with that? All right, so then 495. Well, I'm going to start here. Then I rotate around. Once I get back around here, that's 360, right? And maybe you didn't think you could have an angle even bigger than 180, but you totally can. And so I'm going to subtract 360. If I subtract 360, what am I left with? 135. Didn't we just graph a 135-degree angle? So shouldn't this look the same? But see, here's the thing. Are those the exact same angle? They're not. One's a lot bigger than the other. Right now, they look exactly the same. So the other part of what you have to put on there is your angle or your direction and length of rotation. So you got to have a little curvy arrow like that showing that you started there and went to there. That's 135 degrees. So for this one, I would start here. I go all the way around to 360, keep going, and that's how you distinguish between the two. We do end up in the same spot. So they are called coterminal angles because one just had one extra little loop in it. We'll talk about those more on the back, but it's just like running an extra lap around the track is all that is. Everybody good so far? All right, so then I've got this negative 140. So here is where I start. Since it's negative, I'm going to go clockwise. I know from here to here is 90. So if I add 90 instead of subtracting it so I can figure out what's left, how much farther do I have to go? 50. And that's really close to 45, right? So close, you probably can't tell the difference when we're ballparking it, right? So we're just going to kind of aim for 45, 50-ish, and you're fine. And then show that that's how we rotated, so that you can show that it is a negative 140-degree angle. Okay. Any questions? We all good so far? Have y'all graphed angles like that before and seen angles like that? Nobody? Okay. I wasn't sure. I always threw in some extra stuff that I thought was important because I knew where you were going with all this stuff. All right, but that's okay. But I mean, it's been a while, you might have forgotten anyway, but we all good on all that? Even if it makes you feel a little uncomfortable because you got negative angles now? All right, so now let's talk about radians. You do talk about radians in geometry. Again, it's not a huge part of geometry. It comes in with arc length and when you are doing circles and stuff. I don't even think you talk about it with trig, even though that's why we need it, because it makes sense where you do it in geometry, though, with arc length. And that's because of what a radian is. So I'm going to explain it to you, and then I'm going to show you a little animation that does better than my little drawing up here. But so we have this circle, right? So this is my radius. The length of the radius is whatever it is, it's r. If I take that same length and wrap it around the circle, now my red line segment and my red arc, those have the same length. Okay, so when the radius and the arc length are the same length, then this angle right here is just 1 radian. It's 50-something degrees. It doesn't matter. You're never going to have to know that, but it's kind of good to know it's 50-ish. I mean, kind of looks 50-ish, maybe, whatever. But you don't necessarily have to know that. But what if it doesn't stop here? What if it stops here, right? And it's actually longer than the radius. Well, to find it, and the reason that you talk about it with arc length in geometry is that the radian measure is the arc length divided by the radius. Okay, and that says that over here somewhere. A radian unit is a unit of angle measure based on arc length. I guess that's all it really says. 1 radian is defined as the measure of the angle formed when the radius is equivalent to the length of the intercepted arc. So that's 1 radian, but in general, it's the arc length divided by the radius, okay? So let's look at this real quick, and then I'll put this back up here. So we have a radius here. I'm gonna see if it'll let me drag this. That's what I was afraid of. Okay, there we go. And we're gonna draw a circle, okay? There's my radius, there's my circle. Then I'm gonna take that radius, and I'm going to bend it around the circle so that it makes an arc, kind of like what I just showed you. Okay, so now that red arc is the same length as the radius. And so then there you go, that's 1 radian. Okay, so if we copy that, and that 1 radian gets copied here, well, maybe. There's 2 radians, 3 radians, oh, 2 radians, 3, 1, 2, 3, oh, 3, oh my God, 3 radians. Now 3 radians is almost 180 degrees. How many radians do you think 180 degrees actually is? Pi. 3.14159. 180 degrees is pi radians. Bam. Bam. There we go. Okay, there we go. Pi radians, which means if I go all the way around the circle, how many radians do you think 360 is? I just said it. 2 pi. Oh, no, 2 pi. Yeah, so pi radians and then 2 pi radians. Circumference of a circle is 2 pi r, right? That's kind of where that came from, why it is, why everything is what it is there. 2 pi radians. So pi radians is 180, 2 pi radians is 360. Okay, it's a different measurement. You can measure angles in degrees, radians, and gradients. Radians are a thing. They're kind of obscure, and you only use them for very specific things. I'm not even sure how much they're used anymore. The only reason I even know they exist is because there's a button on an old calculator that I had. But I'm not sure that they're really even used anymore. So, all right, so let's go back over here. So what we know is we know that 360 degrees is 2 pi radians. And we know that means 180 degrees is pi radians. Now, units are a very important thing, right? To put the degree symbol on angles when you have degrees, to put centimeters on things, all that good kind of stuff. But radians technically don't have a unit. So like I put it there, but it's usually written more for clarification. Okay, and here's why it doesn't. So remember I told you that you're going to take the arc length and you're going to divide it by the radius. So let's say that our arc length is 10 centimeters. And let's say that our radius is 5 centimeters. Okay? Well, then the units cancel each other out, right? And then 10 divided by 5 is 2. So my answer is 2. Not 2 centimeters, not even 2 radians. It's just they're kind of dimensionless, which seems weird. But so you might see it written, like if you see it written like that, it's mainly, again, for clarification. But we don't actually have to put the units and stuff on there. Sometimes we just do it to make it make sense to ourselves, so it's not just something random. Okay? So when we convert, there's these little converting formulas, but I'm going to show you how we know which way to do it. This part right here is what you want to keep in mind, is if there's 180 degrees to pi radians. If you can keep that, you can do that. We need to know how to convert, and we do it a little bit, but we don't necessarily do it a ton. Okay, it's just like a very minor part of what we do and understand the concept there. So if I'm going to convert 60 degrees to radians, the first thing we're going to do is identify what quadrant that's in. 60 degrees would be in which quadrant? Which one? 1, because it's between 0 and 90, right? It's somewhere there. I'm not saying that's where it is, but it's in the first quadrant. Okay, so we're in quadrant 1. Then I'm going to take 60, and I'm going to either multiply by pi over 180 or 180 over pi. So you got to ask yourself, what are we trying to get in there and what are we trying to get rid of? That's 60 degrees. I need to divide the degrees out, right? Which means I need the degrees in the denominator, and I got to put the pi in, so that needs to be in the numerator. Okay, doing it the reciprocal, you'd have something over pi, and although that's not unheard of, especially in something basic like that, that just wouldn't make any sense for us right now. Then we just simplify, can cancel out those zeros. Then this 6 over 18 becomes 1/3. We do not write 1/3 pi, it is pi thirds. It's always all in one fraction. Okay, everybody okay with that? Any questions at all? Okay. So 160, what quadrant is that in? 2, okay, because it's going to be like right before 180, right? So we're in quadrant 2. So I'm going to take 160, I'm going to multiply it by pi over 180, cancel the zeros out. So 16 over 18 reduces to what? 8 over 9. So this would be 8 pi ninths. And I don't think I'll make you a believer today that radians are better than degrees, but I promise you very quickly next week you'll be on board with me. You might be a little on, you might decide you are okay getting on board before we leave today, but all right, so negative 330. What quadrant do you think that is in? We're right here, so we're going to go clockwise, right? 1, because it's, well, not all the way like that. If I go all the way, it's a negative 360. So it's just 30 before that, or 60, 30 before that. So we are in quadrant 1. So I have that negative 330. I'll multiply it by pi over 180. Cancel out the zeros. Don't forget my negative, right? Can divide those both by 3, so that'll be negative 11 over 6. Any questions at all? All right. Now, when we convert from radians to degrees, we are going to decide on our quadrant before we convert, which means I'm going to push you out of your comfort zone. And I highly, highly encourage you to approach your assignment this way too. I mean, you don't have to know the quadrant to be able to do that. But if you actually listen to what I'm saying, which y'all aren't because you're talking to each other, if you actually listen to what I'm saying, all this will make really good sense very quickly. And if you think about things the way I'm trying to get you to think about it, it'll all make sense a whole lot better next week when we start going through the unit circle. Okay? So when we are, and my plan was, and I guess I didn't do a very good job of this, obviously, because y'all don't have any room at the bottom of your paper. And my intention was for you to have a little bit of room. And you don't even have that much room in the margins. So you don't need a whole lot of room, but on the margins, I'm going to do it down here so I don't have to scroll. But what I'm doing, you try and cram it in any little blank space you have, because I think it might be helpful to have it on there. I apologize if there's really no room. Or maybe at the very top, whatever works. But so we know that for a circle, okay, we start out here at 0. We know that this is pi radians. And then we could get all the way around to 2 pi, right? So 90 degrees in radians, what do you think that is? Pi over 2, good. Pi over 2. All right. So I'm going to say over and over again that you need to think fractionally. Now, don't let the fact that it has the word fraction in it let your mind shut down, okay? Because it's not maybe what you think. But if you can think fractionally, but by whatever these fractions are, you'll be able to break this stuff down and make sense of it. So since I need to figure out what this is, which is not crazy hard, but I'm just going to use this as an example to show you how the rest of it's going to work. So this is 0, this is pi halves. This is actually 2 pi halves, right? Because I did 2 times 90. And isn't 2 pi halves the same thing as pi once you reduce it? Okay, so if I think fractionally, I have 0, pi halves, 2 pi halves. What would this be? 3 pi halves. See how easy that is? I didn't have to actually add fractions or anything. And then that 2 pi is actually 4 pi halves. So if you can think fractionally around the circle, you'll be able to make sense of these radians, right? And it's not nearly as scary. It seems a little overwhelming at the beginning, but we're going to be fine. So let's look at this number 7. This is 18 as the denominator. So I know that this is pi, but I can also think of this as 18 pi over 18. Isn't that the same thing as pi? Would you agree with that? So if this is 0, then what would this be in terms of 18s? 9 pi over 18. You see how that works? So then what quadrant is 5 pi over 18 going to be in? 1. See, you don't fully understand radians, or I'm not saying you don't understand what they are, but like as far as having a good concept of the values, that's okay that you don't. But being able to reason through that, that's clearly in quadrant 1. I'm not asking you, what do you think the value is? No, we don't really care about that. We're about to figure that out. But nobody would expect you to be able to just estimate like that. That's not necessary. So now I'm going to convert. So I have 5 pi over 18. I need to get the pi out of it and get the degrees in. So I'm going to multiply by 180 over pi. So then the pi's cancel out. And then 18 goes into 18 once, goes into 180 10 times. So I just have 5 times 10, which is 50 degrees. And that is in the first quadrant. So you kind of check yourself in the end anyway. Any questions at all? All right. So now let's look at negative 11 ninths. So that means this would be 9 pi ninths, right? This could be 0. And it's negative, so if I start here, whether I go positive 9 pi ninths that way or negative this way, I can just make it negative, that's fine. So if this is negative 9 pi ninths, where do you think a negative 11 pi ninths is? In the second quadrant. And this would be like 4.5 pi ninths, which we would never actually write that way, but for you to think that way to make sure that, or I'm sorry, well, yeah, so it would be negative 13.5, but we wouldn't write that. That doesn't make sense as a fraction, but as far as values are concerned, for you to figure out where things are, it's totally fine. We're in the second quadrant. All right, so negative 11 pi ninths, we're going to multiply by 180 over pi. So my pi's cancel out. 9 goes into 9 once, goes into 180 20 times. So I get negative 220 degrees. Any questions at all? Before the end of next week, you're going to be able to tell me like that what quadrant 7 pi thirds is in. I don't expect that right now. Don't expect that at the beginning of next week. But right now, I expect you to be able to figure it out at this point. So that's what we're going to do now. This is thirds. So this is 3 pi thirds, right? And obviously that's 0. If I keep going all the way to 2 pi, what would this be in thirds? 6 pi thirds. Okay. Well, this is 0, 3 pi thirds, 6 pi thirds. So where do you think 7 pi thirds is? First quadrant, exactly. Okay. That makes sense to you? And the question did come up today, is it always going to be twice as much? And yes, because it's always pi and 2 pi. So this would be negative 18 pi ninths. This would be 36 pi 18ths, right? It's always twice as much as whatever the denominator is. So 7 pi thirds times 180 over pi. I'm going to cancel those pi's out. 3 goes into 3 once, into 180, 60 times. So it is 420 degrees. Any questions at all? We good? So knowing how to convert is important. We're not going to know your radian measures. We're not going to convert every single thing in our head. That makes no sense. That's just like one little skill that you need to kind of understand. And you don't always have to, you'll get to the point where you don't necessarily, and maybe now, you don't necessarily have to write it out, but you want to think it. I'm writing it so I don't lose you and you can kind of see what I'm telling you to think about. All right, flip it over. So this says, find an angle theta coterminal to the given angle where theta is between 0 and 360, or between 0, and that should say 2 pi. I keep forgetting to change that. 2 pi, because it's one rotation. So I use this phrase on the front. So coterminal angles. If I want to end up here, I can start here and go a positive pi halves, or I can start here and go a negative 3 pi halves. Either way, I end up at the same spot. I could also make another lap and another lap and another lap, right? And I could do another lap the other way. You know, we could all start right here. By the time I get here, some of y'all would be here. Some of y'all would have made a couple laps already, but we'd all end up in the same spot. Just like if we were all going to go to the mall right now, we could all leave out of here. Every single one of us take a different route, end up at the same spot. That's all that's happening. And because it's circular, you can do that. You can't do that with linear links. So since it's one more rotation, if we're talking degrees, I'm either adding or subtracting 360 every single time, right? Because that's one rotation. Does that make sense to you? So if I'm already at 544 degrees and I need this to be between 0 and 360, I'm not going to add 360. But if I subtract 360, 544 degrees minus 360 gives you that theta is 184 degrees. So you can rotate 184 or you can rotate 544, you end up in the same spot. That's what coterminal means. The prefix co means with, and terminal meaning like you're terminating. Okay? So this negative 170, it's negative. I need it to be positive between 0 and 360, so I'm going to add 360. And that's going to give me that theta is 190 degrees. Any questions at all? All right, so now on to the radians. If I can add or subtract 360, what do you think I add or subtract to get to do these? 2 pi, right? But because our denominator is a 2, if we want to think of fractionally, the value of 2 pi, but with a 2 in the denominator would be what? 4 pi halves. Good. So I'm going to, so for 11 pi halves, so let's think about this again. This is pi halves, this is pi, this is, this is 2 pi halves, and then this is 4 pi halves. So 11 pi halves is clearly more than 2 pi, right? That means I need to subtract 4 pi halves. That gives me 7 pi halves. 7 pi halves, still bigger than 4 pi halves. So I got to do it again. And that gives me that theta is 3 pi halves, which is actually right here. So when I'm right here, if I rotate around again, I'd be at 7 pi halves. I rotate around again, I'm at 11 pi halves. So all three of these, this angle, and this angle, all land you in the same place, but this one has the value between 0 and 2 pi. Okay, we good with that? All right, so now on 13, it's negative, so we want to add 4 pi halves. So that would give me negative pi halves. Still not positive. So I'm going to add 4 pi halves again. And that gives me that theta is 3 pi halves. So negative 5 pi halves, negative pi halves, and 3 pi halves are all the same, just like this. So again, to get right here, I went this, kept going that way, but I can go negative pi halves and then go around again. That's negative 5 pi halves. Okay, they all land you in the same spot. Any questions at all? All right. Now I've said multiple times, and I will continue to say it, that we don't really care about degrees, and then I keep putting degrees stuff on here. But again, it's because I know that's kind of what makes sense in your brain, and I need to make sure you understand the concept, and then you also understand how to do it with radians. So we'll drop all the degree stuff here pretty soon. But in order for us to really understand the unit circle and be able to know it in the manner that we have to know it, reference angles, super important. So so for an angle theta in standard form, the reference angle is the positive acute angle, that should say formed, by the terminal side and the x-axis. So your reference angle is always positive, it's always acute. Now, it's not always in standard position, which means that I don't care which direction you rotate to make that reference angle, because it's a reference angle, it's always positive. So whether you're rotating clockwise or counterclockwise to get the angle, it's still the reference angle itself is going to be positive, all right? And I'll kind of keep reminding you of that as we go through this. So this says to sketch each angle, then find the reference angle. All right, so we're going to sketch 150 degrees. So we're here. We're here. And then this is 90. And then I'd have to go how much more? 60. And 60 is how far through the quadrant? 2/3. Very good. So I'm going to go about 2/3 of the way through to make that right there. And then I'm going to label this. This is theta. And that is 150 degrees. Okay. Now over here, that's what I have here. This is theta. We rotated it. It almost kind of looks like it's maybe the same, but it's not. There's my theta there. The reference angle is positive acute and made with the terminal side and the x-axis. It is the shortest way back to the x-axis. Our generic term for any angle is theta. Our basic term for any reference angle is alpha. And so to draw the lowercase Greek letter alpha, it looks like this. It's kind of like a fat Jesus fish. You know what a Jesus fish is? I don't know what, they have a real name, but something like that. Looks like he ran into the wall. So it's not a lowercase a. Make an attempt to make it look like an alpha that's got two little tails that go off, but it doesn't have to be fancy. Again, you're just making your attempt. Okay. So then that means that this here is my reference angle. And so here alpha would have to equal how much? 30 degrees. Because that would have to make 180, right? Any questions about that? Okay. All right, 315. So we're starting here. 315 would be in which quadrant? 4. And so it's going to rotate all around. How much farther would I have to go to get to 360? 45, which tells me I can draw this right in the middle there. So that right there is theta, and that's 315 degrees. So then my reference angle right here, okay, we already have the answer. What is it? 45, yeah? Like I kind of had to figure it out to know where to draw it, right? I mean, I could have subtracted and gone the other way, but there's your reference angle. And I'll explain to you once we get to the radians, like why they're so important and why we even care. All right, so the negative 240, we're going to start here. If I go negative 180, I go to here, then I would go how much more? 60. So I got to go another 60, which is about 2/3 through there. Like, not about, it is 2/3. And then this is theta, which is negative 240 degrees. And then this would be your alpha. And alpha would be what? 60. And it's a positive 60, even though we were dealing with negative stuff, because the reference angle is always positive, always acute. Okay, we good on that? Any questions? All right, so let's move on to the radians. Now again, here's what I don't want you to do. I don't want you to convert that to degrees, figure out where it is, and then draw it, because I want you to start thinking now about how these radians work. And you can even label this a little bit. So this is 5 pi thirds, which means that for pi, that would be 3 pi thirds. You agree with that? Because that is pi. And then if I go all the way around back to where 0 was, what would that be in thirds? 6 pi thirds. Okay. So 5 pi thirds would be in which quadrant? The 4th. So we're going to do everything with the horizontal axis, with the x-axis. If you can get to either side of that and then go up 1 or down 1, you'll be able to figure out where you are. Just do everything with this, and you either go up or down, and that'll make more sense what I'm saying after we do that. But so I'm going to go back. I'm going to have to go back pi thirds. So one thing that you do need to know, okay, even when we drop degrees, every now and then we relate stuff just because they've made so much sense to us for so long, just to have actual values in our brain. A couple of ones that we need to know, a few of them. Well, pi halves we already know is 90, but we need to know 30, 45, and 60. Those are your special angles. Remember our special right triangles there? We need to know what those are in radians, and then everything else is just gravy. It just comes along with it, okay? So 90 is pi halves. 45 is half of 90. So what do you think 45 is in radians? Pi fourths, exactly. And then 30 is pi sixths, and 60 is pi thirds. I'll explain to you more later about why those are what they are. Right now, just have that to refer to. And all this is really going to help us do is know where to draw these things. Like we know it's in the fourth quadrant, but if I'm going to go back pi thirds, that means I'm going back 60 degrees. That's just going to help me with my angle. So I'm here, and I got to go back 60, so it's about right there. So this is where theta gives me 5 pi thirds. This is my alpha. And what do you think alpha is? Pi thirds. Okay. What questions you got? Okay. All right, so then we have 13 pi sixths. So that means we're going to think in terms of sixths, which is difficult to say. So this would be 6 pi sixths. This would be what? 12 pi sixths. So what quadrant do you think 13 pi sixths is in? 1. So we're going to start here. We make one full rotation and then go another pi sixth, and pi sixth is 30. So I can put it right about there. Go all the way around like that. And so theta equals 13 pi sixths. Okay. Your reference angle right here. Now I think this is the first one that we've had so far where my reference angle, to get back to the x-axis, I go clockwise. Doesn't matter, because it's the reference angle, it's always positive, it's always acute. What would alpha be here? Pi sixths, exactly. Everybody good so far? Any questions about the process? Please ask me a question, tell me to repeat something, whatever. Okay. So then we're here. And that's fourths, so this would be 4 pi fourths. That would make this 8 pi fourths, except they're negative, so we can just make them negative, and it still works because of where they are. I'm going to start here. Since it's negative, I go clockwise to end up here, which means I should end up in the second quadrant. And pi fourths is how many degrees? 45, so we're right there in the middle. So theta equals negative 5 pi fourths. My reference angle, shortest way back to the x-axis. This is alpha, and that is pi fourths. Always positive, always acute. Now, let me show you one tiny reason, because there's lots of reasons, but here's one tiny reason that you're going to like radians more. Because remember when I told you, you're just going to have to be able to give me values. Not only are you going to have to tell me what is the sine of pi fourths, what is the cosine of pi thirds, whatever. You're also going to have to be able to tell me what is the sine of 13 pi sixths, 5 pi thirds, like quickly. You have to just know it. No figuring it out. I mean, maybe thinking through 1 or 2 steps, but no like calculating in your brain. But the thing is, we do everything through the reference angles. If you know everything you need to know about pi thirds, congratulations. You know 99% of what you need to know about 5 pi thirds. Okay, so just like I told you, once we learn sine, cosine, and tangent, we think of the reciprocals through that lens, so it's not 3 new sets of stuff. Same thing with this. Once we get our reference angles down and we really get those, then the rest comes pretty naturally. Okay, we good so far? So here's one tiny reason that these are better. Look at this. This has a denominator of 4. My reference angle is pi fourths. Denominator of 6, my reference angle is pi sixths. Denominator of 3, my reference angle is pi thirds. Will happen every single time for our special angles. If we're thinking degrees, it don't work that way. You'd have to know where you are, how many rotations you made, and actually subtract, and there's not that pattern. I mean, there's patterns, but not as obvious of a pattern. You with me on that? So one of the many, many reasons you're going to be glad that we're just flushing degrees down the toilets. Okay? Any questions at all? Okay, so because I do have a second, because somebody came back and said, because we're not done, but she was like, I don't understand why these are what they are. And I was like, well, I didn't technically explain it right now, but let me kind of do that down here. So you understand that pi fourths is half of pi halves, right? But if I'm here and I have, this is pi halves, or 90, and this is 0, if I cut it into thirds, which you can pretend like that's thirds, so we'd have 0, 30, 60, 90, right? So that means that I need to think in terms of thirds, basically. If this is pi, if this one right here is pi 6, and then I'm thinking, and if I'm thinking fractionally, this is pi 6, this is 2 pi 6, which means that is pi thirds, and then 3 pi 6 reduces to pi halves. So each one of these little steps is pi 6, and that's why it works that way. And you got to keep it straight in your mind that 30 goes with pi 6, and 60 goes with pi thirds, and then you'll be fine. No big deal. Any questions at all on this stuff? All right, so we've talked a lot about quadrants. We're going to live and die by our quadrants, but what if it's not in a quadrant? Because on a lot of these, the first question I'm going to ask you about something like 13 pi 6 is what quadrant is it in? Because you have to know that. If you don't know that, then you knowing anything about pi 6 is completely irrelevant, okay? But that won't be so bad either. But what if I ask you about pi halves? What quadrant is pi halves in? Well, it's not, right? So they're called quadrantals. So if you have, when the terminal side of an angle that is in standard position lies on the x or y axis, it's a quadrantal angle. So if you're at 0 or 2 pi or 4 pi or negative 4 pi or whatever, that's a quadrantal angle. Or if you are at pi halves, anything that lands on the axis, those are quadrantals. So if we come up with an angle and pi halves is the option, I go, okay, what quadrant is it in? It's not really a trick question. Your answer is it's not, it's a quadrantal angle. Does that make sense to you? Then you have to know it's quadrantal, but like where is it on your little circle there? Okay. Any questions at all? I highly, highly, highly encourage you to get this assignment done this weekend so that on Monday, when we're going through the rest of this, you will have kind of exercised your mind a little bit with this stuff, and I think it will help you greatly.